This is our group project, Flight Data Analysis. In 2019, flight delays cost $32.9 billion alone in the US. To address these costs, past studies have attempted to find the most common factors. One study found that some common factors such as overscheduling, late check-ins, technical failure, and many more were the cause of this. Along with those factors, they also found that the two most significant consequences were financial loss and terrible customer experience. A similar model was done for flight delays that attempted to predict weather-induced delays. They used different models such as decision trees and random forest, which we will be attempting some. Another model used a support vector machine model to analyze flight departure delay, where they showed a correlation between factors such as pushback delay and taxiout delay to flight delays.
For our data, we use a Kaggle dataset named Flight Status Prediction. This dataset consists of flights from January 2018 to July 2022, with 1,571 unique airlines, 4 to 8 million flights, and each flight consisting of 60 different features. This visualization describes the percentage of flights delayed for each month of the year. We see that the early months of the year and the later months of the year, except December, have lower percentages of delayed flights. There is a spike of delayed flights in the middle of the year as well as in December. This data makes sense, as the summer months and the holiday season are typically busier months for air travel. This visualization describes the percentage of flights delayed versus the departure time of the flight. We see a higher percentage of flights delayed in the early hours of the morning, although this falls to about 20% at 5 a.m. and then begins to rise gradually over the course of the day, peaking at 50% around 9 p.m. to 10 p.m.
So as we discussed, flight delays cause problems for millions each year, costing both customers and airlines. Our goal in this project was to develop a supervised model that can make accurate predictions about the delay status of a flight. This would allow travelers to reliably check the status of their scheduled flights and plan their travel more consistently and with less anxiety. For our midterm, we stripped out redundant information, dropped all rows that had nans in them, used lasso and sequential feature selection to pick out our final features, and tried both one-hot and ordinal encoding for our categorical variables. For our final models, we used all of the same things as our midterm. For the data cleaning, we stripped both our redundant rows and dropped out all nans, and we decided to use only one-hot encoding and normalized our periodic values with sine and cosine functions. We then equally sampled the number of delayed and on-time flights so that our training set had no imbalance. Finally, we ran PCA on our numerical data and combined it with our one-hot categorical data. For our two midterm models, we had two main attempts, one with ordinal encoding and one with one-hot encoding. And we used two different models, a neural network and a ridge classifier with the ordinal encoding. We found that both failed in this case. And what did end up working is we used a ridge classifier with our one-hot encoding, which we found a little bit more success. We had an accuracy of 70%. Here on the right, we can see some of the different graphs from that last run with 70% accuracy. We have a graph of the false positive rate versus the false negative rate, our recall versus our precision, and our confusion matrix.
One of our goals with our project was also to attempt regression models similar to our classification models. This didn't work in the end, as the regression models we tried, which were two, ridge regression and random forest regressor, both didn't give very good scores. The best R2 score out of both models we tried was only 0.09, and that was with the random forest regressor. Next, we decided to try random forest. So first, we experimented using only the numerical data. So we used PCA to reduce the data, and the best results we obtained was when we had no depth restriction and used 100 estimators, which gave 69% accuracy, but overfitted to our data. We also tried to train a random forest on the entire data set, no depth restrictions, 100 estimators, and the trees would only stop growing if the remaining samples were pure at the leaves. And this yielded 55% accuracy. if you look on the right, it does a lot better classifying delayed flights as delayed, but it's not very good at discriminating on-time flights. Almost half of on-time flights it would classify as delayed, which isn't very good. We found that training took too long for us to effectively cross-validate the optimal number of estimators, as one run could take almost half a day. So we turned to other faster ensemble models with similar characteristics.
Another model we discovered when searching for improvements for random forest was the histogram gradient boosting tree. And this model utilizes decision trees in an ensemble format similar to random forest, but it's much faster to train on large data sets than both regular gradient boosting and random forest trees. In addition, because of this faster training time, we were able to use a special kind of grid search called halving grid search to help optimize a few of the hyperparameters. In the end, we achieved an accuracy of 67%, which is slightly worse than our original ridge regression. But looking at some of the graphs on the right, it's clear that our model actually improved significantly in other ways. In particular, the area under curve and the average precision of our model increased drastically over that which we got in the midterm. And in conclusions, we don't think regression worked because we think there's too much variance on how long a delay will be given a specific problem. And there are also so many different kinds of issues, including weather, mechanical issues, crew delays, and airlines even struggle to predict their delays with much more data than we have access to. One-high encoding does perform better than ordinal encoding, but we suffered from high dimensionality, which made training our models quite difficult, especially due to the high memory requirements. And we think that there could be potential improvements to the histogram gradient boosting model by performing cross-validation and grid search over the entire set of hyperparameters, just instead of a few that we selected due to time constraints.